Welcome to qnawire.
This is Chapter 22, Problem 6 from the Sears and Zemansky's University Physics textbook. The cube in figure E22.6 has sides of length L equals 10.0 centimeters. The electric field is uniform with magnitude E equals 4.00 times 10 cubed newtons per coulomb and is parallel to the XY plane at an angle of 53.1 degrees measured from the positive x-axis toward the positive y-axis. What is the electric flux to each of the 6 cube faces, S1, S2, S3, S4, S5, and S6? And what is the total electric flux through all faces of the cube? All right, so first thing I've done is I've sketched out the cube as shown in the figure. S1 is the left side, S2 is the top, S3 is this right side, S4 is the bottom of the cube, S5 is the front of the cube, and then S6, which is the hardest one to represent, is the very back of the cube. I've also drawn the electric field. It's not shown in the diagram, but I've shown that in blue. The electric field is parallel to the XY plane as shown. So we imagine it's going parallel to the plane formed by the X and Y axes, but it's at an angle of 53.1 degrees measured from the positive x-axis going toward the positive y-axis. So we can see that angle, which I've shown as theta, is 53.1 degrees. So that's the angle as the electric field is going stemming out from the z-axis. So it's uniform through the cube, so I've just sketched a couple of the electric field lines for illustrative purposes. So our basic definition for electric flux is what we're going to use for all 6 sides. The electric flux is simply the electric field multiplied by the area of each side times the cosine of this angle phi. And phi is the angle that is between the normal to the surface and the direction of the electric field. So we need to just figure out what phi is, because that's what's going to change for each of the sides. So with this basic definition, well, we know the electric field in each case, it's uniform, 4.00 times 10 cubed newtons per coulomb. And we know the area of each side, it's a cube, so it's just length times length. So the area is L squared, allowing us to rewrite the electric flux as EL squared times the cosine of phi. So we just need to repeat this calculation right here for each and every one of the sides. I'm not going to write this out for each and every one because it's just plugging in. E, the electric field, is always this value that we're given, and L is always 10 centimeters. And make sure to convert to meters from 10 centimeters each time that you are computing this calculation right here. So we always want to make sure we're in standard units, so we will just rewrite this basic one here as that's the same thing as 0.10 meters. So make sure to use this value each time, since we're working in newtons and coulombs, so everything needs to be in standard units. All right, so EL squared is the same for each one, so the only thing that will change is phi for each one. For surface S1, which is on the left side, well, that phi is our angle here, 53.1 degrees, because that's how far we are, but the normal to S1 is pointing out in the negative y direction. So that's 90 degrees from the x-axis. So we have 53.1 minus 90 degrees to get the angle phi. And that gives us the electric flux then on side 1 is negative 32 Newton meters squared per coulomb. For side S2, which is at the top, the angle between the electric field and the normal to the surface, which is in the positive z direction, well, that angle is 90 degrees. But the cosine of 90 degrees is 0, so there is no electric flux going through S2. And it's going to be the same thing for S4 as well. S4 is the bottom one, exact same calculation. the angle is 90 degrees because it's going straight down the negative z direction. So again, the flux through S4 is 0. For side S3, which is on the right side here going straight, in this case it's flipped from S1, so it's going to be 90 degrees minus 53.1 degrees. So we use that angle, plug that in for phi to give a positive 32 Newton meter squared per coulomb. And then for S5 and S6, the front and the back, for S5, which is going in the positive x direction, the angle between the normal to the surface S5, that normal is along the x direction. So the electric field is at an angle of 53.1 degrees, the angle that we're given. So we plug that angle in for phi to get the answer of 24 Newton meter squared per coulomb. And then S6, well, we go in the negative x direction because we're going out the back of the cube. So that's starting at 180 degrees minus 53.1 degrees, which gives us the negative answer that we got in S5. So we get a negative 24 Newton meter squared per coulomb. So these values then give you the total flux going through each and every one of the sides. Part B is very simple. It's just what is the total electric flux through all faces of the cube. Couple ways you could do this. First, you could just know that the total flux through the cube must be 0 because any flux that enters the cube must also leave. So it doesn't matter what side it comes through. The total sum of all electric flux, since the electric field is from outside the cube, then the total electric flux must be 0. Anything that goes in must come out. Or you could also calculate, just add together the electric fluxes for all 6 surfaces. So we'd have negative 32 plus 0 plus 32 plus 0 plus 24 plus negative 24. And that total sum gives us 0 as well, if you wanted to do so mathematically. So the total answer then is just 0 for the total flux. There is no total flux because everything remains balanced out.